Hello everyone, welcome back to Calculus. This time we are moving to our third big topic of calculus. As I said before, calculus it is the study of three big things: limits, derivatives, and integrals. And so far we are getting to the point of our last big topic, integrals. And for now, we are in section 4.10, it is antiderivatives. And well, if you are confused, I would say you may want to consider antiderivatives. They are just integrals. Antiderivatives are integrals. And we will clarify the difference between antiderivatives and integrals in a moment. Okay, so first, let's just work on the textbook, section 4.10, antiderivatives. What is an antiderivative? To clarify the concept, I have a relative simple example. We consider a function, actually two functions. One function, it is denoted by the lowercase f, which is 3x squared. The uppercase f, it is x cubed. And also I put a constant there, okay? The constant could be of any number. And you will see why I want to put this constant here. Because with or without this constant, or it really doesn't matter, for any value with a constant, the derivative of this uppercase f, it is always the same, 3x squared. The derivative of the uppercase f, it is always the lowercase f. So based on this observation, okay, as I wrote here, we can write in this fashion, and then we can say the derivative of the uppercase, it is the lowercase f. And also from the other side, okay, in an equivalent way, we can say the antiderivative of this lowercase f is the uppercase, or specifically, I'm saying the antiderivative of 3x squared is x cubed. And also, as I mentioned earlier, with or without this constant, when we take this derivative of x cubed plus constant, it is always 3x squared. So I'm saying, really, given a function, there are many antiderivatives. And also, it's worth to mention those antiderivatives, they differ by a constant. And in writing, we write the antiderivative of this lowercase f with dx in the end, or specifically, this is the antiderivative of 3x squared dx. It is x cubed plus an arbitrary constant, or simply it is the uppercase f. Okay. And another thing to mention, this integral sign. I say this integral sign, really it is for the English letter S. And very soon you will see an integral, indeed it is a sum, and an antiderivative, it is the integral. So we are using this integral notation, which is a long elongated s. Why? Very tall s. I call this as a long s, because the integral, really, you want to consider integral as a long sum. It's a huge sum. It's infinite sum. Okay. The antiderivative of the lowercase f is the uppercase f. Certainly, for the specific case, as I just explained, we can say the antiderivative of 3x squared is x cubed plus an arbitrary constant. Be very careful about writing. We say the antiderivative of 3x squared. In writing, we have the integral sign first, and then put the function there. Then you have dx in the end, okay? Dx in the end, and then we will explain the situation again. This dx, actually, has an actual meaning. Actually, I think 1 or 2 weeks ago, we have a concept of differential, and you may want to consider dx as an actual quantity, which is differential. 3x squared dx should be considered as 3x squared times dx, or in the general case, it is a function times dx. Okay. Integral, it is sum of function times the differential of x. So we write antiderivative or integral in this fashion. And this part, it is a more generalized version. Antiderivative of function, okay, it is the lower uppercase f. And then if you understand clearly how do we say the derivative and how do we say the antiderivative, really, my understanding, the antiderivative formulas, they come from those so-called derivative formulas. So I try to list some important formulas, at least for now, we need to know them very well. And indeed, actually, I tried to list both the derivative formulas and the antiderivative formulas. This is the derivative power rule. And then accordingly, we do have the antiderivative power rule. Antiderivative of a power function, what you can consider here is increase the power by 1 and then put the reciprocal of the new power before that x. And also the anti-differentiation power rule, you may want to know there's an exception. This power R cannot be -1. Two ways to think about the case, R cannot be -1. Indeed, R, if it is allowed to be -1, this formula really won't work because R plus 1 will be 0. And more importantly, you really want to consider the second formula, because when R is -1, we know the derivative of logarithm, natural logarithm, is 1 over x. So you just simply say antiderivative 1 over x, it is log n of x. And also, to be precise, we do have the absolute value notation for the notation x, for the variable x here. And also, this is very important to note. Otherwise, I guess sometimes it is not possible to calculate the antiderivative. Okay, integral if you don't know, if you don't have the absolute value notation part. And another formula, anti-differentiation, involving with the exponential function, because derivative of the exponential function is itself. So roughly, you can say the antiderivative of the exponential function still is itself. But don't forget the arbitrary constant in the end. And also, accordingly, we have the anti-differentiation rules for sine, cosine. And also, this is a formula I really want to tell you for now. We may not use this formula a lot. But anyway, if you need to move on to Calculus 2, Calculus 3, or some other advanced math classes, and you really need to take a note on this formula. Okay, it comes from the derivative of the tangent inverse, which turns out to be 1 over 1 plus x squared. So accordingly, the antiderivative of 1 over 1 plus x squared is tangent inverse. So these are the basic formulas for antiderivatives. Put in a simple way, I'm saying they are literally from the corresponding derivative formulas. Think very carefully. All the antiderivative formulas come from the corresponding derivative formulas. How about let's take a quick look at some examples, very simple examples. Okay. First one, I have the antiderivative 1. And you may want to say this may not fit any situation in the formula that I just mentioned. We have x, there's no x. But you can consider this 1 as x to the power 0. So it does fit the situation for anti-differentiation power rule. X to the power 0. Increase this power 0 by 1, that's x to the 1. The reciprocal of the new power still is 1. So simply put, I'm saying antiderivative 1 is x. And don't forget the arbitrary constant. Okay. From now on, I may not mention the arbitrary constant in the end specifically, explicitly, but you want to know there is always an arbitrary constant for any antiderivative. Then antiderivative of x, this is x to the power 1, using the anti-differentiation formula. Increase the power by 1, that's 2. The reciprocal of new power, that's 1/2. Antiderivative of x squared, increase the power by 1, that's x cubed. The reciprocal, that's 1/3. Similarly, x to the 3. And then take a quick look, what about 1 over x squared? The thing here is you want to understand we cannot apply derivative rules or really anti-derivative rules somewhere in the middle and jump to the denominator directly. Anti-derivative power rule really works for the anti-derivative of some single power functions. So you want to recognize 1 over x squared as x to the power of negative 2. This is a power function. Then from here, you apply the anti-differentiation power rule in the same fashion. But you want to know the power really it is negative 2. So when this negative 2 increased by 1, that's negative 1. The reciprocal of negative 1 is still negative 1. Okay. And then antiderivative 1 over x cubed, it would be x to the negative 3. And then increase negative 3 by 1, and then the reciprocal of negative 3 added by 1, that's negative 2. I just figured out I needed to fix this part. This should be considered as negative 1 over 2. Yeah, negative 1 over 2. And then also we need to have this negative 1 over 2. And in the end, we still have this 2 in the denominator. Anti-differentiation power rules. And again, well, we did 1 over x squared, 1 over x cubed. You may want to take it for granted that it will work for the same fashion of 1 over x. It is x to the negative 1, but then remember, a moment ago, we mentioned the antiderivative 1 over x, indeed it is logarithm. And also, indeed, we do know it is the absolute value of the logarithm. There's absolute value notation here. Logarithm of the absolute value of x, antiderivative 1 over x. Okay. Little more about anti-differentiation power rule. What would happen to the antiderivative square root of x? You cannot jump inside the radical notation to get the antiderivative. What you can consider here is, remember in calculus, in derivative, we always consider square root of x as x to the 1/2. And then this is the power function I'm talking about, x to the 1/2. The power r, it is 1/2. Then using the same anti-differentiation power rule, increase this 1/2 by 1, get the reciprocal to the front. 1/2 plus 1, that's 3/2. The reciprocal, that's 2/3. So the antiderivative really it is 2/3 times x to the 3 over 2. And also, I hope you feel comfortable to convert from radicals to rational powers, or in both ways, really in both ways. So x to the power 3/2, it is really the same as x times square root of x. Antiderivative of square root of x is 2/3 times x times square root of x. How about let's take a quick look about antiderivative 1 over square root of x. You really don't want to say it's the reciprocal of that thing. Simply it is not correct. As we discussed earlier, okay, we are considering the anti-differentiation power rule. So 1 over square root of x is considered as x to the negative 1/2. The power r here, it is negative 1/2. Then add it by 1, negative 1/2 plus 1. This coefficient before x, it is always the reciprocal of the new power. Okay, so negative 1/2 plus 1 turns out to be 1/2. The reciprocal of 1/2, that's 2. So I'm getting the antiderivative as 2 times x to the 1/2. And hopefully this one is a lot easier to convert back to a radical. It is just 2 times square root of x. And also we do have an arbitrary constant in the end. So this is the discussion of section 4.10, antiderivatives. Thank you for watching. I'll see you next time.